Hello everyone. Last months were very busy for me and my puppet master. I'm sorry, that's why I'm a bit late on my tutorial schedule. In spring, I had the chance to participate to several events, like Touchdesigner summits in Berlin and Amsterdam. My puppeteer performance was pretty bad, of course, but mine was great. Always a pleasure to meet this wonderful community. And I've already tested the Touchdesigner alpha version provided in Berlin and spent some time playing with it. You've probably heard about the new pop family which is coming soon. I have to say, it will be very powerful, for sure. The example projects, including those of YFX Lab, are very impressive, showing how complex things can be done in pops. That's being said, older techniques can still be achieved, of course. So, today, a tutorial about creating a versatile particle system inside Touchdesigner, with only texture operators, so using the extreme performance of your graphic card, instead of your processor. Why? Because it's much faster, that's why, you jackass. All particles on the videos you see behind me were made with the exact same logic. Some of the project files are available on our Patreon for quite a long time now. Yeah, I hear you. I know there are already plenty of good tutorials online about this. And I know my puppeteer already shared some project files with this kind of technique. But, for your information, he keeps receiving a lot of similar questions about those files. And I ended up with this radical decision. Move your ass, make a tutorial, and let the world hear some essential theory. To be clear, I'm not doing it for you, but for me instead, to stop all this shit. You want to know more? Don't move. The others can leave right now, I don't care. Oh, I forgot to mention that this tutorial is perfectly compatible with the one-on-point cloud manipulation I released last year, and which you seem to have liked. We will also see today how to emit particles from any 3D object, but this obviously includes photogrammetry data. And actually, even on 3D Gaussian splatting. I encourage you to cross the techniques discussed in these two videos, and your work will only be better. As I said, before building a full particle system in TOPS, we will start, as usual, with some nice theory. A particle system can be described as some points moving for some time, before spawning back to their original location, then, do it again, and again, for infinity. And yes, not at the same time, preferably. Let's imagine we have only one particle in 3D space. Its coordinates are represented as RGB colors, one for each axis, in a texture of 1 by 1, so only 1 pixel. In this particular case, the image is black. It means it stands at the origin, so its coordinates are equal to 0. And for now, it is not moving either. Lazy ass. Forces. We want to affect some forces to this point, by slowly adding some RGB values. And we get a new position data. We will explain in details later, but this type of operations can be inserted inside some feedback loops to obtain some more natural behaviors. So basically, at each frame, a small amount of color is added to the previous image calculated. That's why we call it loop. Constant rays means a linear translation. Indeed, if we add the same value every time, it's moving in straight line. More disturbed data, such as noise, will rapidly become less predictable. The problem is, if you wait a little bit, your point will probably be very, 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 very far. And that's an issue. And it's time to introduce the lifetime. We add another pixel, acting like a switch. As long as the particle is alive, and the death condition is not fulfilled, our point will be affected by our forces. While this one is white, the loop is on. But as soon as it becomes black, hop, it will restart from its original birth location. Forces are back, the particle will live its lifetime, get back to original position, and so on. Do you see that? Now, if we have a bigger texture, with more points coordinates, the same system will act like a particle system. With one problem, all the points will respawn exactly at the same time. Fuck. We need to create an appropriate lifetime texture. There are plenty of ways to do that. The very first time I saw this kind of technique was in the old but amazing tutorial by Marcus Heckman from Derivative in his Napoleon video. Supermarket Salad also recently shared a great life component. But here's one method, with the easier logic you can think of. It can be drawn like this. Wait a minute. I probably have to stop acid. I see fractal recursion everywhere. Oh, okay. Yeah, I see. It has an amount of life duration. Every frame, it's getting older. The countdown loop is on. It's getting older again. When the amount is 0, the particle die. It get affected a new life duration. And the whole process restart, over and over. It really looks like your human cycle of life, no? Without the rebirth part, I guess. And the trick is to distribute different amounts of time to each one. That's mean. I love this. Now we have that, we can use this as a life image. Don't worry, we will see how to build that system just with pixels and nodes in a minute. Now, the particles are acting like expected. Perfect. Masking. One important thing to notice here, now we have multiple points, is the ability to apply effects only on specific points instead of all. For that, we will see different ways on creating black and white mask selections. For example, with the emission, only certain parts of our object can emit points, while others don't. Same thing with the forces, which can be accumulated, each one influencing some points and not others. Okay, enough talking. I think it's time to dive inside the software now. This is what we are trying to achieve here. We have 3 images, which are the initial data. An image for the position, one for the emission mask, and the last one for the color. This base is the full particle system, and at the end, we have everything we need to instance some geometries. For now I will delete this geo to keep only what I need for this tutorial. A very simple render system with a camera, some lights, and a render top. Plus, a basic geometry for the colored X, Y, and Z axis. Let's create a new geocomp and call it particle system. Inside, we can delete the default torus. Another geocomp, called teapot. Let's now import a 3D object from our hard drive with the file in SOP. In my case, the well-known teapot. I use a transform SOP to align it with the world's axis. Yeah, I'm a little bit of a maniac, I know. You don't really have to follow the few next following steps, but I want my model as a reference in wireframe. So wire SOP. Let's plug it inside a new geocomp. A PBR material and assign it. Okay. To create some random points onto the surface, we use a node I love very much, the sprinkle SOP. Let's choose 500,000 points for now. We need to convert it as a chop, so SOP to chop. Then as a top with the chop to top. The data format is RGB, and we choose to fit to a square image. Now, an out top. Create another null called init position. As I said earlier, we need few more things. Because we would like to emit particles from everywhere, for now, a simple white constant top will do the trick. I choose the set resolution only option. Then, a second null called emit mask. Same thing for the color. A gray constant top is enough for right now. Plug it into a null top called init color. A little bit further, let's create 2 null tops, called position and color. A geometry comp, for the incoming instancing process. Inside, delete the torus. Create an add SOP. Turn on the add points parameter. Then a convert SOP, and convert to particle per point. At the end, a null SOP, with the render and display flags on. Go to the instance page 1. Drop the position null in the translate op, then fill the fields with according channels. A, R, G and B. On the second page, same thing with the color data. Create a line mat. Apply it. We don't need lines but points. Okay. Between the initial data and the final data, add 3 null tops. Right-click, collapse selected. Rename this base particles. Inside this base, this is where the fun part begins. Select the first two nulls, then collapse selected again. Call loop this new base. Another null top, then collapse selected again. Call this one forces. Insert another null top. This one will be the end of our loop. I choose for it a nice yellow color. Go inside our loop base. Create a feedback top. To easily reset it, we will use the classic keyboard in Chop. I want the 0 key of my numpad, then drag the channel on the reset pulse parameter of the feedback. The last thing to finish our loop is the end loop null inside the target top parameter. Great, the loop is on now, but we don't see anything for now. We have to add some forces. Go to the forces base, delete the nulls, and add a noise top. Monochrome off, offset to 0, small amplitude. Connect the position data to it, to be sure to have the right numbers of pixels. Choose the output to noise only. And, important thing here, do not forget the second input also to get a noise depending on our position data. Create an add top, and plug the two images together. Wow, what a mess. Adjust the noise parameters to get something nicer. Press 0 few times. Okay, good. Now we need to create the lifetime system. To create the appropriate lifetime image, remember, we need set up a cycle of life and death. Go to the loop base. Create a null top here. Both position data and emission mask data will be needed. You will understand why in a minute. So, select the two null tops, then collapse selected. Call this new base, life. Dive in. Insert a first base here. Create another null top, and another here. Then collapse these two nulls together. You will obtain another base comp. Indeed, the final life cycle is composed by two important concepts. The countdown, that makes particles spawn, then undergo age, to finally die. And the emit mask, to choose where particles will be emitted. You can understand this as some places where the particles are constantly dead, without even rebirth. These two conditions will finally be multiplied with a multiply top before going out with an out top. Let's start with the countdown. Create a constant top. Set resolution only. We want it to be 32 bits, mono. You can choose the normalized split option to know its value. Create a math top. We would like to multiply it by the lifetime of a particle. In this case, 300. Create a noise top. Offset to 0 and the type to random. Because the particles are aging, we would like to subtract these two. Subtract top, and this operation should be applied every frame in a loop. So, feedback top. Create a mad top. It will act as a switch per pixel. Choose for that the luminance. Switch inputs to 1. Now, for our condition, create a threshold top. Threshold to 1. 8 bits, mono. That's important, because mad top are acting weird when the mask is deeper than 8 bits. Okay, drag the subtract top onto the feedback top to finish our looping system. We see something is happening. A new keyboard in Chop. Key 1, to reset this feedback as well. Right now, the emit mask is still white. That's okay. We will talk about it a bit later. Create a null top. Normalized split view. We don't need RGB values, but one channel instead. You can easily set this multiply top to follow the depth of the input one. Okay, nice. This null represents the whole life of all of our points. We will use this data later. Insert a threshold top, less or equal comparator, value 1. And force it to be 8 bits, mono. Go outside. Create a new matte top. Original position in the first input, feedback position in the second, and our life image in the third. Choose luminance and switch inputs to 1. We have something better here. Okay, I think it's time to be a little more creative with our forces. Go back to the forces base comp. We will see different things here. First of all, let's apply a mask to our first noise. For that we will use a threshold top on the position image in order to affect points differently depending on their position in space. Comparator less, green axis. Increase the soften parameter. Insert a multiply top. Okay. Now, only the highest particles will be affected, you see? And also, I love when forces also has influence on color. For that, create a level top. Choose a color. Then, an add top. Great. Another important note here is the point transform top. And this one is a little bit different because it can be masked directly with the second input. This one will allow you to make classical 3D transformations, such as rotation, scale, and so on. Do not forget it, it's very powerful to obtain very complex behaviors. Last thing, please remember also that forces can be accumulated. Okay, now, few adjustments about the look of our particles. Go back where your instance geometry is. Create a PBR matte. Then apply it. Inside, create a box SOP. A transform SOP and scale it down. Connect it to the null. We can also, optionally, create a SSAO top to add some fake contact shadows. It's often better to visualize it alone, to adjust it like you want. That's nice. If you'd like to go further, now let's talk about particles' rotation and scale. Indeed, if you now change your particle type as a scaled box, like this one, you will easily see the issue. We want them following their trajectory instead of this. Rotation. One easy way to orient your particles is to compare their current location with the position they had the frame before. Basic vector mathematics teaches you that a simple subtraction is enough to get the vector size, also called magnitude, but also the direction. We will use this value as the rotate to vector parameter. Scale. There are many ways to play with the size of particles. For example, using the magnitude recently obtained. The greater the distances between the frames, meaning the point is moving faster, the longer its size will be. Not a bad idea, and also, a common thing in particle systems is the ability to define some size over life. For this, we will use a lookup top. It will allow to find the size correspondences for given life values. The size can decrease over life to be 0 at its death. It's often better, visually. Go into our particles base. Make some space here, because we would like to make further calculations outside of our main loop. Create a null top. Then collapse selected. For the rotation, create a cache top. Small cache size, 3, for example. Then, a cache select top. Cache index to -1, which means the frame calculated before. Let's make the difference with a subtract top. We don't need the alpha in this operation. Create out top. Now, for the scale. I'm used to create two S-curve chops. First from 0 to 1, and the other from 1 to 0. Create a join chop, plug everything. Right. Create a null chop. Then a chop to top. We need to get our point's life situation inside the null we previously created in the life component. Create a select top and drag it. Create a lookup top and set the depth to 8 bits. In the range parameter, it should be from 0 to our maximum life value, here, 300. Then, another out top. Outside, create two another out tops. Outside again, two null tops. The first one is named rotation, and the second one, scale. In our instance page, drag the first one to the rotate to op parameter. R, G, and B, and the forward direction is positive Y. Oh, look at this. The second null should be used as the scale operator with only R channel. This is beautiful, isn't it? We're almost there. It's finally time to play with the emission mask, remember? Right now, particles are emitted from every polygons of our object. Go to the emission mask base we created a while ago. You will understand how we can use our position data. Create a threshold top. Green axis for now. And play with the different parameters of this threshold. And, of course, the axis can be changed as well. You need a radial mask? No problemo. Create a constant top. It will act as the center of our sphere. A subtract top. Be careful, I choose the input one as fixed layer to have the right amount of pixels. A math top. Combine channels with length option. Set it as 32 bits mono. Another threshold top. Now, play again with the parameters. Last but not least, create also a noise top with both inputs connected. Noise only. Hell yeah, it's working. For the last thing I want to show you, bring back the original mask image and go outside to our main network. On my Patreon, I posted some time ago a small tool to convert any 3D object as a point cloud. It even takes the texture of the model. If we take this component, here's what we got. In my case, I have an octopus model. Let me just deactivate the previous teapot, I don't need it anymore. Plug everything into our nulls of initial data. And you know what's great? We can simply use an RGB keyer on the image texture to define some emission masks. Look at this, particles are only emitted from the brightest parts of the texture. I love that. If you're still there and feel a little bit overwhelmed by everything we see together today, just know my puppeteer already shared a pre-built versatile particle system. He tried to make the component really fast and easy to use with custom parameters. You will find it on our Patreon page, where it's available to download for contributors only. A huge thank you to all the people who support us on the platform. This is what makes these tutorials possible. A special shout out to my top-tier contributors, you rock guys. Every comment or criticism is more than welcome. That's it for me today. I'm out.